All right, so before we get to example 6, we're going to define one last thing here in this section. One type of angle. It's called a reference angle. And the key word in reference angle is reference and angle. They're both key words, right? So we're going to refer to what a reference angle is quite a bit. Now, you had reference angles back in geometry. So before I tell you what it is here in Precal, if you had a right triangle, you had something about like hurting your foot and needing to like repair it by soaking your toes or something. I don't know. You remember that? Sohcahtoa? What was that for, Sohcahtoa? Sine, cosine, and tangent. Yeah, we're going to meet those guys here pretty soon. But they referred to opposite sides and adjacent sides, right? And that was pretty particular depending on which non-90-degree angle you were referring to, or to which you were referring, right? So if you let this be the angle to which you're referring, then this becomes the side opposite, and this becomes the, well, that's still the hypotenuse. It's an adjacent side, but it's the longest side. So we say that the adjacent side is the non-hypotenusal adjacent side, correct? But it's depending upon referring to that angle. If you looked at a different angle up here, we'll call it alpha. The hypotenuse is still the hypotenuse, but what happens with your opposite and adjacent? They flip. So it really is important that you establish the angle to which you're referring first. And that's what we're doing here. We're going to call it the reference angle. All right? I'm going to give it a subscript name, just like I did for the coterminal. So theta subscript REF. That means reference angle. It's a positive acute angle. Can a reference angle be negative?
No.
No. It's a positive acute angle. Can a reference angle be obtuse?
No.
No. It's got to be a positive acute angle. All right? That measures the angle between the terminal ray, and what? The closest x-axis. Okay, let me show you what I mean. We're drawing our angles now in standard position, which means we have an initial ray that always starts where? Which side? The positive x-axis. Okay, so if I rotate all the way around to here, that's going to be some angle that's between 180 and 270. That's the angle itself. Okay, let's just give it a name. What's a plausible name for an angle like that? I'll give you the name. 225. Is that plausible? Sure. Okay, thank you. Good. So 225 is a plausible measure for that angle. Is that the reference angle then, too? No, because the reference angle has to be positive and acute. And acute means what? We didn't mention that, but good looking because it's less than 90. All right. So 225 is not acute, right? Is it obtuse?
Yes.
What does obtuse mean?
Greater than 90.
Greater than 90. Yeah, okay. So, can't be the reference angle. What did I say the reference angle was? It was the positive acute angle that measures the angle between the terminal ray. Here's the terminal ray and the closest x-axis. Where's the closest x-axis? Over here? No, there's one right here. See that? So I guess the reference angle would be this right there. And guess what? That is right. That is the reference angle. I'll shade it right here in green. So if you want to call that theta subscript ref. Any idea how we can find that? I have an idea. Do you have an idea? I want to figure out what that angle is. There you go. Subtract 180 from 225, because if the angle theta gets us all the way to the terminal ray, and the reference angle is now effectively the distance or the measure of the angle by which I've gone past 180 to the terminal ray, then the reference angle is going to be 225 minus 180, which gives us what? 25? 45. Yeah, 45 degrees. So the reference angle is a 45-degree angle. Very good. What if I wanted to have an angle in quadrant 2 that had the same reference angle measure of 45 degrees. Could I then figure out what my angle, which I'll call maybe alpha, would be? How could I figure out that? What would that angle be? 225 minus 90? Oh, because they're both 45? Yeah, that would work. Is there a way to measure it off the x-axis?
180 minus 40.
There you go. If you work off the x-axis in general, like if I didn't know the other one was down there, you could do 180 minus 45, because now I want my terminal ray to stop short of 180, yes? Because the terminal ray is going to be falling short or greater than 180 in quadrants 2 or 3, we're going to be working off the x-axis, which is 180 degrees. So 180 minus 45 would be 135 degrees. So what would be the reference angle for 135 degrees? 45. What would be the reference angle for 225 degrees? 45. Very good. So there's two different angles now that have the exact same reference angle. Are there any other angles between 0 and 360 that have reference angles of 45? Yes, there's one down here in quadrant 4. If this reference angle here, now notice if that's the reference angle, we're measuring it between the terminal ray and the closest x-axis, which is now the positive x-axis. If I want that measure right here to be 45, what would be the angle that gets us all the way around, stopping 45 short of a full rotation? Very good. 360 what? Minus 45. Yeah, which is 315. So what would be the reference angle for 315? 45. Very good, because there's 45 to go to get to a full rotation. Now, if there's a reference angle of 45 in quadrants 2, 3, and 4, I guess there has to be one in quadrant 1. What would be the angle then in quadrant 1 that has a reference angle of 45? What would be that angle there? 45, yeah. It would be its own reference angle, yes? Because what do we know about every angle that lives in quadrant 1? That's between 0 and 360, within one positive rotation. It's a positive acute angle, yeah. So every angle in quadrant 1 is its own reference angle. But if you fall in one of the other quadrants, the angle can't be its own reference angle, but you can find it, right? Just by working off the x-axis. You're either like, ooh, I'm short of 180, I just went past 180, or I'm short of 360. So working off the x-axis is very important. Let's try out a fun example. Example 6. If beta is negative 265.363 degrees. Is that in decimal degrees or DMS? Decimal. We're typically going to work in decimal degrees, just an FYI. Part A, draw beta in standard form. Okay, draw beta in standard form. That's step 1. All right, negative 265 means we're starting on the positive x-axis, which we don't even have to draw the initial way. And we're rotating how? Clockwise or counterclockwise? Clockwise. So, in which quadrant will beta terminate? 1, 2, 3, or 4. Right. It's going to be one of those. Let's see. We got 90, 180, 270. Oops, that was too much. So it's going to be somewhere in here. And I'll label that as beta. So it does live in quadrant 2. Now, again, I'm not going to get out and measure to see where in quadrant 2 it lives. So as long as you draw in quadrant 2, you're fine. Whether it's closer to the x-axis or y-axis, it's fine. Part B, find the reference angle beta subscript ref. All right, well, let's draw the reference angle first. Is the reference angle this angle right here? No. Do you think anybody in the history of Precal has ever thought that was the reference angle? Yeah, one person, and I won't give you that person's name. George. No, it wasn't George. No, a lot of people do, but that's not what the reference angle is, right? The reference angle is the angle between the terminal ray and the closest x-axis. So this right here, shaded in green, is the reference angle. All right, so I'm going to go ahead and call that beta subscript ref. Now the question is, how do we find its measure? Guess and check. Subtract, yeah. We've gone past 180. We've gone past 180. So the fact that it's negative, that's just a vector that tells us to rotate clockwise. The magnitude of the angle is what we're really after here. So if I take the magnitude of the angle, which is 265.363, all I have to do then, since I've gone past 180, is determined by how much I've gone past 180. So if I subtract 180 from there, I get 363. I get a 5 here. I get an 8. Now, is my reference angle supposed to be positive or negative since my original angle was negative? Positive, because the reference angle is never not what? No, it's never not positive. Double negative, sorry. It's never not positive, which means it's always positive. Yeah. Good. It's always positive. Always positive. Beta subscript rep is 85. Very neat. Okay, part C. Find the coterminal angle, beta subscript cot, that is 47 positive rotations away. 47 positive rotations away from beta. How are we going to do that?
Multiply by 47.
Take beta and multiply it by 47? Very good. I got to take my angle, negative 265.363 degrees, and I have to add something to it. And what I'm adding is 47 full positive rotations. So if you remember the definition yesterday, it's going to be multiples of full rotations. How many degrees in a full rotation? 360. So it's going to be plus 360 degrees times 47. Now this is where the calculator can be very, 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 very helpful. We're all out up here. I'll go ahead and do it up here so we can follow along. Negative 265. You want to get in the habit of always writing down first on your iPad or paper the expression that you are going to be typing into your calculator. Write it down first because you always have to show me what it is you're doing, and then you can write the answer. So it ends up being this wonderful number right here, 16654.637. Now it's customary if your answer is given, or your question, is given to you in decimal degrees, to give your answer in decimal degrees. And if your question is giving you an angle in DMS, you give your answer in DMS. So this would be an acceptable answer. So this angle here and the angle beta, they're not the same angle, are they? But they terminate at the same place, don't they? They share a terminal ray, which is why we call them coterminal angle. So what would be this angle's reference angle? Very good, 85.363. So we can kind of make a little observation here then that if coterminal angles always share a coterminal ray, regardless of how they get there, if the reference angle is always the positive acute measure between the terminal ray and the x-axis, every single coterminal angle in the whole wide world, they share the exact same reference angle, right? They share the exact same reference angle. Okay, just for review, let's convert this angle into DMS, all right? We'll convert the coterminal angle into DMS. So the 16654, it's going to stay there. And then what you're going to have to show me, we'll practice for the quiz, you'll have to show me that you're taking point 367, and to convert that fraction to minutes, you multiply it by what? By 60, right? That's all you'd have to show. So up here, 0.637 times 60. And it's going to give you the number of minutes, so it's 38.22. Okay, so what you could show me then is you show me the result, 38.22. But now up here I'm going to put 38 full minutes. And then you're going to show me that you're taking the 0.22, the fractional part of the minute, multiplying it by 60 to get the seconds. 0.22 times 60. And you get 13.2. So at this point, if you end up with a decimal, you're just going to go ahead and report. If it doesn't terminate, bless you, you're going to report 3 decimals on your seconds because we're not going to go down to any other unit smaller than seconds. So you will possibly have a decimal in your seconds in your final unit. And if it goes on for more than 3 decimals, round or truncate. So there you go. La, 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 la. Well, it says to round to the nearest second. I guess I should follow the instructions. So that would be 13 seconds if you don't want to put the 0.2. Okay, reference angles. Very important. Let's try another one here, a bonus one. I'm going to let you do it, okay? Let's come up with an angle alpha. And let's do 5, 7, 6, 3, 2, 8.1 degrees. Here's what I want you to find. I want you to find, first of all, the coterminal angle between 0 and 360. I guess I should say this, okay? That's within 1 positive rotation. And then I want you to find the reference angle. If I didn't ask you to do number 1, and I just asked for number 2, you would probably want to do number 1 on your own, because finding number 1 makes it a lot easier to find number 2. Feel free to use your calculator for this one. This makes a great quiz question. Mine's a little bit of what we did yesterday. There's always pooping dogs. What a great view. Anyone get it? You got it? I'll come over there and check. See. Yeah, you got 32. Did you round, or did it come out to be perfect 32? Interesting. Okay, let's see. Did you type in the 0.1 at the end of the angle? Oh, yeah, you didn't put the 0.1 there. Yeah, right idea. Right idea. You have it. If you would have put the 0.1, you would have had the right answer. You got it. Yeah, I just threw that 1/10 of a little piece on there just to make it a little more flavorful. There you go. All right, let's see how to do this one here. Potential quiz type question. You got a very large angle there that's probably more than 1 rotation, right? I'm just guessing. That's bigger than 360. Yeah. So what we said yesterday then, rather than just subtracting 360 multiple times, as exciting as it was, we have a new, more efficient way to do it, right? We take the 5763281, and I'll show the work down here. We take the 57632.8.1, and we divide it by what? 360. That's the number of degrees in 1 rotation, and that should give us the number of rotations. So 5, 7, 6, 3, 2, 8.1. So it's very important to double check when the numbers are this big to make sure you've typed them in correctly, because you don't want to have the right process down and then use the wrong numbers. So that gives us 16.911. That means that we are making 1,600 full rotations in what direction? Yeah, these are positive, so counterclockwise rotations. We don't care about those full rotations. Now, here's the part that you don't want to mess up on. You don't want to just then go to the next line. We're interested in the decimal part. You don't want to type in 0.911389, because this is not a terminating decimal necessarily. Your calculator is storing numbers probably beyond this last 9. It's just not showing them. So what you do is you just say subtract the full rotations or add them back if it were negative. And now watch, more decimals appear, don't they? So it was storing them. That's what you now want to do. So let me show that here. We'll subtract the full rotations, and you're left with 0.911388888. So it looks like it's a repeating 8 at the end. And that's going to be the fraction of a rotation. That's now what we want to remultiply by 360 degrees to get where that lands within one rotation. So now if you just hit times 360, you get this, 328.1. And if we had started with a negative angle, then remember that would still be negative. To get the coterminal angle between 0 and 360, we would just add 360 one last time. But that one is the coterminal angle, so I'll go ahead and label it that. They share a terminal ray. Now 328.1, we have a little bit better understanding of where it lives. Which quadrant does it live in? 328? Yeah, it's over here in quadrant 4. It's just short of 360 degrees. All right, so that's your theta coterminal. So now we need to find the reference angle. Remember, this is your reference angle. It's the positive acute angle between the terminal ray and the closest x-axis. Looking at now where it terminates, it's pretty easy to determine how to find the reference angle, yes? Your reference angle is going to be what? Very good. 360 would be a full rotation. We subtract from it 328.1, and on your calculator, since it's there, you can just hit 360 minus, and you can hit second negative to recall the answer. Oops, but you got to type in 360 minus the answer, and you get 31.9 degrees. So there's your reference angle, 31.9 degrees. I saw that on several people's iPads, so that's good. Reference angle. How many other angles within one positive rotation, other than 328.1, have a reference angle of 31.9? 3 others. Very good. There's always one in each quadrant, right? There's going to be one in quadrant 3, one in quadrant 2, and of course the one in quadrant 1 we know right away is what? 31.9. Every angle in quadrant 1 that's between 0 and 360 is going to be between 0 and 90, and therefore its own reference angle. Okay, you got that down? Kind of fun, right? Especially with a calculator. Without a calculator, whole different ballgame. Not so much fun. All right, so we've been measuring our angles in what units? Degrees. What are the units of degrees? Degrees, right. And we use the de Grubel symbol, right, to denote it. There's another way to measure rotation. And if you've been in a physics class, you probably already know about it. It is a unitless measure of rotation. So it's not going to have any units, which is actually preferred when you're doing applications. Okay? That unit of measure, which is really not even a unit at all, it's just more of a description, we're going to call it a radian. Y'all heard of a radian? I hope so. A radian is a derivation on what key word do you reckon? Radius. Okay? Yes. And a radian is very closely related to the radius. Okay? Its definition is tied intimately to the radius of a circle. So here's what a radian is. If we look at a circle, doesn't matter how big or how small, let's just call the radius of the circle r. R can be big, it can be small. It can't be 0 though, right? Then we don't really have a circle. So as long as r is some positive number, we're going to trace out the circle here. We are going to then take the length of the radius for some predetermined circle, whatever it is, and you're going to wrap the length of the radius around the circumference of the circle. So if you take this length here and you pin it down here on the positive x-axis, this is where we start in our standard notation, and if you wrap that radius around the circumference, it's a finite length, right? So it is going to end. And let's say it ends right there. Okay? This is also the radius, but now it's curved. If where it stops, you draw a line back to the center of the circle, you will get what's called a central angle. In general, that's what we call them, because it's in the center of the circle. And that central angle theta we define to be 1 radian. We say here that theta is equal to 1 radian, and we abbreviate it rad. Not to be confused with the movie from the 80s where the guy was on a BMX bike trying to do a backflip. That's a different rad. Okay? 1 radian. Okay, so that's a pretty appropriate name then for that angle, because it's exactly 1 radius length around the circumference of the circle, drawn back to the center. Okay? What would 2 radians look like? Well, good question. If I take another length of the radius and I wrapped it around the circumference and I kept going, it might land right about there. If I drew a line back to the center, like this, then this angle would be 2 radians, and we could call that theta. 2 radians. If I did it again and I took another length of the radius and wrapped it around the circle, it might land right about there. If I then draw that line back to the center, guess what we would call the angle that rotates all the way around, stopping just short of 180? We would call that 3 radians. I'm just going to write this as 3r here. I'll call this 2r just to make it a little bit easier. Okay, theta equals, theta equals, theta equals. All right, well, I can keep going. This is kind of fun. Let's wrap another length of the radius around there. Here we go, wrapping another length of the radius. Somewhere right in there. That looks reasonable. Right there. So that angle that's going to get me all the way from the positive x-axis all the way around to that terminal ray, that's going to be 4 radians. Do it again. La, 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 la. Right about there. That's going to be 5 radians. Do another one. La, 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 la. That's going to be 6 radians. And do I have enough for another length of the radius? No. I have some left over here. Not enough for another full length of the radius. So, and this is a nice property of circles. Around any given circle, regardless of how big or regardless of how small, you can always wrap 6 full lengths of that radius's circle around its circumference. The circumference is going to be made up of 6 full lengths of the radius, always plus a little bit more than a quarter of another one. Just a little bit more than a quarter of another length of the radius. That's true for any circles. Because notice, if the radius gets bigger, the circumference gets bigger in direct proportion to the size of the radius. They're both linear measures. Okay? Now let's define what that theta is. Okay? The theta we define right here. A radian is going to be the measure of the central angle of a circle subtended by an arc. Ooh, that's a key word. Subtended. What does sub mean? Sandwich? Below. Good, good. So basically this angle is going to be below the arc that I was drawing. That's an equal in length to the radius of a circle. In general, because we're not always going to go just full units of the radius around the perimeter or the circumference, the radian measured angle theta, in standard position is going to be the ratio of the arc length, which I'm going to call S, Okay, and notice it was labeled as S to begin with. It's the distance we actually travel around the circumference divided by the radius r. So we can represent that like this. Theta is S over r, where S is the arc length. It's how far you travel along the circumference, and r is the radius. Now let's see why it's unitless. If it's arc length, what am I going to measure arc length in? Let's say I'm measuring the radius in feet. What would I measure the arc length in? Also feet, because it's the same units. It's the radius. So you get like feet divided by feet. And what's feet divided by feet? Nothing. There are no units there. There are no units there. So what makes this nice is we have a way to represent rotation without having units, so that if we have an application that involves anything that rotates or spins or is cyclical, okay, we can actually apply any units we want on the x-axis and y-axis. We're not constrained by just using degrees on the x-axis, because that's not usually how we reference rotation, okay? You'll see it's going to be beneficial as we move forward in this section. All right, so here's what I just drew for you. You can keep drawing lengths of radius all the way around the circle, and you're always going to fit 6 plus a quarter of another one, all right? We need to figure out exactly what that is. How are we going to do that? Anyone know exactly how many radians are in one rotation? Let's derive it. Let's derive it, okay? What's the formula for the radian measure of an angle theta? S over R. S over R. The easiest way to do it, the easiest way to derive it from given formulas is to look at a full rotation. One full rotation. Okay, I'm going to define this circle to be R. If I go one full rotation all the way around, what would the arc length be? It would be the what of the circle? If I go all the way around once, we call the arc length the circumference, right? So for one full rotation, S, the arc length, is equal to C. So I get C over R. Now, what's the formula for circumference? This is where we kind of have to use some knowledge. What's the formula for circumference? 2 pi r. Okay, that was given to us by Archimedes way back in the day. So the circumference of any circle is 2 pi times r. I divide it by the radius. What happens with your r's? They don't cancel, they divide out. And we get 2 pi. So there you go. For one full rotation, theta equals 2 pi. Well, of course, pi is about 3.14159, yes? So what's 2 times 3.14159? About 6.28. There you go. So you can always fit 6 full measures of the radius plus a little bit more than a quarter of another one. But knowing that one full rotation now is 2 pi radians, we can come up with some conversion factors. Watch this. This is fun. I may have left off a fun. I apologize. Okay, if one rotation is 2 pi, then one rotation is also 360 degrees, yeah? So 360 degrees must be equal to 2 pi radians. What are the units of degrees? Degrees. What are the units of radians? Nothing. Now let's bisect that. What's half of 360? 180. What's half of 2 pi? 1 pi. So there you go. A half rotation is 180 degrees, but now a half rotation is pi radians, which means you can you could fit 3 full radii in a half rotation plus a smidgen of another. Okay? What's half of 180? 90. That was very good. And what's half of pi? We're just going to call it half pi, or pi halves is what we're going to call it. So a fourth of a rotation is pi halves radians. All right, now if we're counting by pi halves, or we're counting by 90, this would be 90 plus 90 is 180, plus another 90 down here is 270. Let's count now by pi halves. This is 1 pi halves. That would be 2 pi halves, right? So down here at 270 we have 3 halves pi, or 3 pi halves as I call it. So 270 degrees is 3 pi halves. And then, of course, if we come down here to 0, 0 degrees is equal to how many radians? 0 rads, same thing. These are called your quadrantal angles, because they terminate on the axes themselves. They don't fall in the interior in any given quadrant. These are ones that you're going to be so familiar with, you might want to memorize them now. 90 degrees is pi halves. 180 degrees is pi. These could also be conversions. If you're ever trying to convert from degrees to radians, any one of these equations will allow you to convert. The easiest one to use is probably one that doesn't have fractions. So I probably wouldn't use 90 equals 2 pi halves because that has a fraction. Same thing with 270 equals 3 pi halves. I could use 360 equals 2 pi, but that doesn't really, that simplifies, doesn't it? So the easiest one to use is actually this one. How many radians in 180 degrees?
3.
How many radians in 180 degrees? Pi. Right. You're confused. 180 degrees is pi radians. Pi radians is 180 degrees. They're the same. What are the units of degrees? Degrees. What are the units of radians? Nothing. Unitless. Because it's a ratio of arc length to radius, and the units always do what? Divide out. They divide out. Okay, so it's unitless. All right, let's go ahead and come up with a formal statement then. Now that you know what a radian is, you might have been in physics, you've been using radians, you don't know why you're using radians, you don't know what a radian is, and you don't know why it's unitless. All those questions have been answered today on this Friday, this National Hat Day, a day on which we can't wear hats because it's against the dress code, so we celebrate elsewhere. When converting between degrees and radians or radians and degrees, you're going to use one of these two conversion factors. These are equivalent to one, they're not equal to one. Now, because radians are unitless, are you going to lose points if you don't write rad after pi? No. Okay. Are you going to lose points if you don't put degrubble after degrees? Yes. Okay. So pi over 180 or 180 over pi. Those are the two conversion factors, depending on which way you want to go. All right. Let's try it out. Convert the following angles, from degrees to radians. Leave pi visible in your answer. All right. 90 degrees. Well, we already know what that is, right? Yeah, it's a half pi. Now, let's see how this conversion factor works. It's a little bit of dimensional analysis once again. If you want degrees to be gone and you have them in the top, then you need to have a factor of degrees in the bottom. If you want radians to appear, they need to be in the numerator. So now it's either going to be pi over 180 or 180 over pi. What is it here? Pi over 180. And of course, the math works out. What's 90 1/80ths? 1/2. So you have 1/2 times pi or pi halves. You either leave it as pi halves or you trim it with the description of what it is, which is rads. It's nice to have rads if it's not really in some kind of rotational context, because pi halves is just a number. If you put the descriptive word rad behind it, you know you're talking about angle measure, right? That's one you're going to want to memorize. 180 degrees, of course, is, it's pi rads. Pi rads. It's actually 3.1415926 blah blah radians, but we leave it as pi. Pi is an irrational number. It's a transcendental irrational number. It doesn't terminate. It doesn't repeat. So we'll leave it in terms of pi. I won't even show the conversion there. 270. This is one you should memorize. Let's not convert. Let's just go for it. 3 pi halves. I'll put rad there because it's rad to write it. That's a what type of angle if it terminates on the axis? Yeah, we call it a quadrantal angle. We'll define that formally later, but it's a quadrantal angle. All right, 360. 2 pi. Yeah, 2 pi rads. Good. 2 pi radians. All right, so those are ones you need to memorize. Of course, 0 is 0. Now we're getting to some interesting ones. 30 degrees. Pi 6. Excellent. Very good. You could get it one of two ways. You could say, 30 is a third of 90, right? It's a third of 90. So it should be a third of pi halves. What's a third of pi halves? Pi 6. You can do it that way. Or you could just convert it, right? Put it over 1 and multiply by pi over 180. Your degrees divide out, and you're left with 31/80, which is 3/18, also known as pi 6. This is another one that's going to be very, very common. You're going to have to memorize this one. 30 degrees is pi 6 radians. 15 degrees, pi 12. That one's easy to get without converting because it's half of 30. Half of pi 6 is pi 12. To take half of a fraction, you either double the denominator or take half of the numerator, if there's a even number up there. 45, pi fourths. That one's easy to get because it's half of 90, so it should be half of pi halves. What's half of pi halves? Pi fourths. But again, if you want to use the conversion factor, when in doubt, use the conversion factor. Pi over 180, that gets the degrubbles to divide out. We're left with pi fourths. Ooh, this one, negative 175.4. By the way, this is one you're going to have to be real familiar with. This one, not so much. So this one we're going to go ahead and use the calculator on. Now, because we're going to leave pi visible, here's how you're going to do a problem like this. You're just going to type in negative 175.4. You're going to divide it by 180, as what you've already written down indicates. Hit enter, and you get this awesome fraction. And I'm okay with everyone using the little trick, right? Math, enter, enter. It'll convert it back to a fraction for you. Math, enter, enter. And that's how you need to write it. Negative 877 pi 9 hundredths. Okay? There you go. Which quadrant does that terminate in? Quadrant 3. Good. We still can think in terms of degrees. We're going to start thinking in terms of radians. And, yeah, go ahead. Yes. Now, the last one here I'm going to sneak in. You multiply by pi over 180. Just because it has a pi in it doesn't mean it's going to be a radian measure. There's a degrubble there. So it's a degree. And this one's real nice and easy. You go like, have a great weekend. 5 divided by 4 divided by 180. I'll finish it up while y'all are turning stuff in. Math, enter, enter. We'll see y'all Tuesday. Don't forget about that little Monday break.